This presentation shows learning from demonstration framework applied to the finishing operations like grinding, deburring and polishing. We addressed the following problems. Automatic adjusting the manually demonstrated policy to the robot's kinematic and dynamic capabilities. How to apply a previously demonstrated policies to different robots and polishing grinding machines. Autonomous improvement of the demonstrated policy. A human demonstrated policy is captured in Cartesian space using 6 degrees of freedom passive digitizer and a universal force torque sensor. The position orientation trajectory is parametrized using Cartesian space dynamic motion primitives. Forces and torques are parametrized with weight sum of Gaussian radial basis functions. During the finishing process, we can notice that humans constantly change point of application with the polishing tool, while robots generally keep this point constant. Humans use natural kinematic redundancy arising from the tool shape, as it is not important where exactly the polished object touches the tool. Additional degrees of freedom arising from this redundancy can be exploited to optimize the robot motion. In order to exploit this redundancy, we model the polishing grinding tool as a serial kinematic chain and consider the robot and the tool as a bimanual robot. For finishing tasks, only relative part of the motion of the composed kinematic chain is relevant. Accordingly, we define relative coordinates and relative Jacobian and control the composed mechanism with following equations. Calculation of the relative coordinates require known contact point between the tool and the treated object. We estimate the contact point using the force torque sensor data. Since the solution is not unique, we applied optimization to solve this problem. The video shows an example of contact point estimation. For finishing operations, forces exerted against the polishing grinding tool should be precisely tracked. For this purpose, we applied Iterative Learning Controller, where the adaptation direction coincides with the last link of the virtual mechanism. In most cases, the force tracking error can be effectively reduced in just few iteration cycles, as shown in the figure. To show the efficiency and performance of the proposed framework, we demonstrated more than 100 faucet polishing trajectories and executed them with and without applying virtual mechanism. In most cases, direct playback failed due to the joint limits violation. On contrary, when virtual mechanism approach was used, the robot successfully executed the demonstrated trajectory while minimizing the joint velocities. We did not encounter any case where the virtual mechanism approach would degrade the performance. Note also how the robot reduced the difference between the demonstrated and the measured forces using iterative learning framework.